I was watching.
Hello.
Hey everyone. How we doing? My plan every day during this time is to just at the very least start on Zoom. Today we'll be on Zoom most of the time, but the very least start on Zoom so that we so that I can kind of go over what we're doing. And I've got this posted as a sticky announcement on there, so it'll just be this same link every day while we're doing this. But the schedule I've got posted today. So Anna, to your question, everyone's lunch is 11:30 to noon. So you've got 10 to 10:40, 10:50 to 11:30, then you got a lunch break, and then 5th is noon to 12:40, 7th is 12:50 to 1:30, sorry. All right, so what I want to do today is I would like to introduce, I got a couple more people here. I would like to introduce the concept of circular motion. So we're going to start with some notes. We're going to talk about circular motion, and then what I'm going to do this time, since I haven't even given you the packet yet, instead of doing a like a syllabus like usual, I'm going to have a daily assignment each day that kind of goes over the types of problems we learn how to do that day. And my hope is to finish my lesson early enough that you then finish the daily assignment before 10:40, the end of the period, so that other than, I can't promise that there will be no homework, but I don't want to throw a lot at you and have a lot of things that you just need to balance while we're doing this. So that's my plan, and we're going to see how that looks. So like I said, today we're going to do some notes, and then we're going to work on the daily assignment. There's a part of the note today that usually I go over, but I'm going to take it out this year. But if you are interested in mathematical derivations, I recorded some bonus physics content. If you want to watch this on your own time, you're welcome to. But that's not required. The other thing that I'm just going to say real quick before I get started, like I said, there'll be the daily assignment. Chapter 4 test corrections are open if you would like to do test corrections. And I would recommend that you get those done before Thanksgiving, just so that it stays fresh in your mind. All right, so notes for today, you can label circular or uniform circular motion. So let me pull up my other camera here. All right, so notes for today. Uniform circular motion. And we're going to find that there are a lot of places where this has application. The most obvious ones might be, we're eventually going to be talking about satellites, right? And whether they're man-made satellites or whether they're things like the moon, or how the Earth goes around the sun, or things like that. So we're going to get into that this unit. But then even some more terrestrial things like how do you turn in a car? Because if you think about turning, what you're really doing to turn is you're just kind of going in a quarter circle, right? So if I want to turn left, I kind of am doing a quarter of a circular motion. So that's kind of the idea for this. What we were originally going to do today in class was we were going to do a lab with my flying pigs. I just want to show you this here. Let's see here, so that you can see what I've got here. So usually to introduce the idea of circular motion, I got these little pigs that are tied to the ceiling. And they do something like this, right? So you should be able to see, right? So you can kind of see that there's a cord on this here, right? And the idea is I want to analyze what it is that makes the pig go in a circle, Okay, so stop it here. So that's what we're going to look at. Turns out you need two things in order to go to a circle, in a circle. First thing, what am I going to say here? I'll just say two ingredients for circular motion. And the first is you need to have some sort of forward velocity. So in our case, with the pig, right? I wish you were here so that you could see it. We would have done a whole lab with this. But the idea was the wings on the pig, the purpose of the wings on the pig is to continue it going forward. These wings aren't providing any lift, but they're making it go forward. So you got to have forward velocity to have circular motion. And the second thing that you got to have is you got to have something called a centripetal force, which is a force directed towards a fixed center. And again, we're going to refer to that as a centripetal force. Okay. I like to think about circular motion as a fight between these two influences, right? You have them both in equal measure. And if one of them starts to take over, you no longer have circular motion. So I'm going to give you an example here. I'm going to show you a YouTube video. Let's see here. Not that one. Get out of my way so that I can click on something. Make sure you can. All right. So you've probably seen one of these at a museum or something, right? Where you put these pennies in here. And the idea is that surface, right? The fact that that surface has a funnel means that you've got a normal force that's giving you your centripetal force, right? But you'll notice you need both things to have circular motion. You have to have the centripetal force, which in this case is coming from the normal force of the bull, but you also have to have forward velocity. You can see earlier in this video when the two pennies, there, you see that when the two pennies knock into each other, right? What's happened is now they've lost their forward motion. So if you lose your forward motion, all that's left is the centripetal force, and you end up going towards the center, right? So I'm going to add a little bit to the notes here. So go back to this. What I want to do here is I kind of want to draw an object that's moving in a circle. So and I'll just draw this object at 3 different locations, right? And each time it is moving forward, right? So I'm going to draw, it's got a velocity vector that is constantly changing direction. And then it's also going to have this thing called a centripetal force, which I will label as FC. And the centripetal force always needs to be directed towards a fixed center. Give me 1 second here while I grab the next demo. So the pennies kind of show what happens if you lose your forward momentum, right? Or you lose your forward velocity. If you lose your forward velocity, where are you going to go? Going to the center. But the other question is, what happens if you lose your centripetal force? Well, if you lose your centripetal force, now all you've got is your velocity, and you're going to go a straight line, right? So I think about this like the David and Goliath sort of slingshot, right? If you think about, if I've got something on the end of a string that I'm putting in a circle, right? It's got some sort of forward motion, but the string right now is providing centripetal force. Now, if all of a sudden the centripetal force leaves, right? So all of a sudden I let go of it and I don't have a centripetal force, what's going to happen is the velocity is going to take over, right? So you have to have both of these things in order to have projectile motion. Okay, what else do I want to say about, or not projectile motion, circular motion. All right. The next thing I want to say about that is I want to give you two equations. So the centripetal force, and usually you can have more than one force that gives it to you. So I'm going to say it's the centripetal net force. So the centripetal net force, and sometimes your book will refer to this as the radial force as well, because it points along a radius, but I prefer the term centripetal force. But net force is equal to mass times acceleration. So we're going to say that the centripetal net force is equal to mass times the centripetal acceleration. So this is one equation for you. And the other equation is the centripetal force, the centripetal acceleration equation, which is v squared over r. Now, where does this come from? Again, because we got shortened time, I don't want to go into this, but I've recorded a bonus video if you're interested on Schoology to figure out why that's the equation. But these are sort of the two equations you need to start out talking about circular motion. So I could do something then like ask you how much force is needed to keep an object going in a circle with a certain speed and a certain radius, and then you could find what that was, right? Okay. Let me think about this for a second. The other thing that's interesting about this, has anyone ever done the demo where you put like water in a bucket? See, again, I was going to do this. I suppose I can still do this. Give me 1 second. Gotta find my bucket that probably we used last for the water balloons. I'm trying to think about where I stashed it. Yes. All right. So, okay, what I got here is I got a bucket. So let me change my camera view. And I'm gonna put some water in this bucket. It's not as fun because you're not here to actually see it, but I'm gonna put some water on this bucket. Just a little bit, right? And maybe you've seen this a demo like this before, or maybe you haven't. But the idea is, can we get the bucket to go in a circle without spilling any of the water? So what I'm going to try and do here, I probably should take that pig down. What I'm going to try and do here is I'm going to try and get this bucket to go over my head without spilling any water. So, ready? Here we go. 1, 2, 3. Right? Okay. So what's happening here, right, is if I can turn it fast enough, right, I can get by without getting any water to leave. Now, I want you to think about why this is, right? So in our notes here, right, we can actually see why this is. And I want to see if anyone can figure it out. What is, I'm going to ask you a trick question. What is the force, or is it a force? What is the force that keeps the water in the bucket? You want to have a thought on that? You can feel free to just enter it in the chat or turn on your mic, whatever you'd like.
Is it the velocity of the bucket?
Yes. And the fact that the velocity wants to stay there. And what makes an object want to maintain its velocity?
Inertia.
Inertia, right? So here's what happens. There's this thing, you may have heard this, this term called centrifugal force. That's not a thing. There is no force that pushes things to the outside of a circle, but there's inertia, right? The idea here is you imagine the water in this bucket, when this bucket's going around like this, the water in this bucket wants to go this way, right? But what happens? Well, a moment later, the bucket gets in its way, right? And now the water wants to go this way. And then the bucket gets in its way again. And then the water wants to go this way, but the bucket just keeps getting in the way. So the idea is the inertia carries the water forward or whatever direction it was going in the circle. But then the bucket just gets in its way. And it gives the illusion that there's some force kind of keeping the water in the bucket, even though there isn't. You can also experience this like when you ride a roller coaster, and when you go around a loop in a roller coaster, you feel like you're being pushed to the back of your chair, right? Or you feel like you're heavier. You're being pushed like down to the outside of the circle. But again, there's no force actually doing that. It's your body's inertia makes you want to keep moving in the direction you're moving, but then the roller coaster car just gets in your way. Okay. Does anyone have any questions about this? Okay, let me show you what I've got here on Schoology. And the idea here is I'm gonna stay on Zoom to answer questions about this. But like I said, instead of doing a syllabus, oops, what am I doing here? Nope. If you go to today's page on Schoology, there's this day 34 assignment. And what I've done is I've just copied 3 problems out of the book. You're lucky because there are actually 5 on the syllabus. I think there might even be 6 on the syllabus, but I narrowed it down to what I thought were the most important 3. And so you need to use the 2 equations we wrote down, right? The centripetal force equation and the centripetal acceleration equation. So you can work on these 3 problems and then submit them. And when you've done that, you are done for the day, but I'll stay here to answer any questions you have while you're working on it. The only other thing that I would say is if you want to, you can also get on to at least your multiple choice to do test corrections on your multiple choice part of the test. So that's posted. There's a link there right here. There's a link to Chapter 4 test corrections. All right. Oh, Malachi, did you find, is that the video?
Yeah, that's the news video that
Got it.
from there.
Well, thank you. All right, so anyway, feel free to jump off and work on that assignment and then jump on as you need to, but I'll just be here to answer questions. So, see you.